Okay. Uh, so Basically today we'll do the week 3 assignment, the previous year assignment week 3. Actually, I am lagging 1 week because I am currently in ISRO for my research purpose. So I will compensate that in this Friday. In this Friday, you will get a notification from the NPTEL team. So in this Friday also there is a class from 6 p.m. to 8 p.m. So I am going to solve the week 3 assignment, which is on the diode basically. So mm,
But sir, now assignment complete OPAM.
yeah, I understood that. I will compensate that in this next lecture. I told you, right? So in this Friday there will be lecture, and then in the next Tuesday there will be another lecture. So
Okay, sir.
yeah. So
Okay.
so you please attend this class. I think that most of the doubts will be cleared. Actually, I know that you have already completed this one, but I will solve this in another perspective. So
Yes.
I think yeah, that will be useful. Yeah,
Okay.
fine.
No issue.
Okay,
No issue.
okay. So in the question one, it is just 1 second. Yeah. So in the question one, it is asking like which of the following plots correctly describes the VO versus VI relationship for the circuit shown in the figure. So this is basically a diode problem. So we usually solve this one like this is a diode. So this is the anode terminal and this is the cathode terminal. So this is the P and this is the N. So PN junction diode. So whenever there is any voltage applied across the diode and that voltage is greater than zero point 0.7 volt, which is the typically the cutoff, that is 0 0.7 volt is known as the cut-in voltage. So it is different for the different semiconductor diodes. If you are using silicon, then this is zero point 0.7. If you use the other material like gallium arsenide, so it will change. So like that. So if Vd is greater than 0 0.7 volt, then this diode will conduct. So the diode becomes on when this Vd becomes greater than zero point 0.7 volt. And this diode model we can equivalently write as R on, that is the on resistance of the diode, which is very small, and this zero point 0.7 volt will appear. So this is the case. Okay, and the diode will be off when this voltage across diode is less than zero point 0.7 volt. So then we can represent this diode structure as a off resistance, which is typically very high. So this on resistance is very small and this off resistance is very high. So you consider this R on is typically near about to 0. So this symbol can be represented as a short circuit. And also if you ignore the cut-in voltage compared to the other voltage, then the diode typically denotes as a short circuit when it is on. And when it is off, then it is typically the R off, which is very large. So you can write as it a open circuit, right? Okay. So in this question it is asked like for the following, what should be the VO versus VI relationship. So if you plot Vi versus T time, that is known as time domain characteristics. If you plot VO versus T, that is the output, that is output input characteristics, that is time domain, output characteristics, that is time domain. But VO versus Vi is also known as the transfer characteristics. That means based on the input what should be the output. So in this question they are asking about the transfer characteristics for this circuit. So typically we are first considering the diode to be off. So case 1, the diode is off. So I am denoting this diode symbol as D. So diode is off. So if the diode is off, then here it is open circuit. So 1 kilo ohm, and then there is 2 volt, and this resistance and this diode is off, that means open circuit. So now here the voltage appears as this is V, and this terminal is positive terminal, this terminal is negative terminal. So in this terminal, node A, the voltage is Vi minus 2. So this is the anode voltage, right? And in the cathode side, this is ground basically. So the diode will be off when, if we call this terminal as node A and call this terminal as node B, when VA minus VB should be less than zero point 0.7 volt. So what is the VA? VA is Vi minus 2, Vi minus 2 minus 0 is less than 0 0.7 volt. That means Vi is less than 2.7 volt. So when Vi is less than 2.7 volt, then the diode will be off, and at that time the output voltage VO will be, we can simply write this voltage as VO, so which is nothing but Vi minus 2. So Vi minus 2. Okay. So similarly, when will be the diode on? The diode will be on, second case is diode on. So diode will be on when VA minus VB is greater than 0 0.7 volt, right? So VA is Vi minus 2 minus VB means 0, which is greater than 0 0.7, which is nothing but Vi greater than 2.7 volt. So 2.7 volt is a transition state from, uh, if the Vi is below 2.7 volt, then the diode is off, and if Vi is greater than 2.7 volt, then it is on. So when this Vi is greater than 2.7 volt, then the equivalent circuit becomes, so here it is 1K, and then a 2 volt, and then there is a resistance of 2K, and then this diode that can be written as 0 0.7, right? What I have already shown. So here we are considering this model where the R on, that is the on resistance of diode, is very small. So representing the diode as with this symbol, right? So it is the cut-in voltage of the diode. Okay. So here it is V1. So it is Vi, it is VO, right? So now we have to find out what is the value of VO. Now the current throughout the circuit can be written as Vi, this voltage Vi minus this 2 volt minus 2 minus this 0 0.7 volt minus 0 0.7 divided by the total resistance, which is 1K plus 2K, that is 3K, right? So 3, that much milliampere, right? Okay. So this current is flowing through this 2K ohm resistor, so there will be certain voltage drop. So the voltage drop across this 2K, so the output voltage is nothing but this 0 0.7 volt plus the voltage drop across this 2K resistor. So that is I, the current flowing into 2K resistor plus 0 0.7, right? So it will be Vi minus 2 minus 2 plus 0 0.7, which is 2.7. So this into 2 plus 0 0.7. So that is 2 Vi by 3 minus 2 by 3 into 2.7 plus 0 0.7. Okay, this is VO. So this is typically the VO. Okay, so we got the two case. So when Vi is less than 2.7 volt, it is coming as VO equal to Vi minus 2. This is the equation. And when this Vi is greater than 2.7 volt, then we get this equation. So now what will be the value of VO when Vi is exactly 2.7? So you can put the value of Vi equal to 2.7 in any of these two equations. Suppose if we put in this, so VO will be 2.7 minus 2, which is 0.7, right? And here also if we put VO equal to 2 by 3 into 2.7 minus 2 by 3 into 2.7 plus 0.7. So these two cancels out, so it is 0.7. So if we plot the graph, so, so this is the output voltage, this is the input voltage. So this is 2.7, 2.7. So whenever the Vi is 2.7, VO is 0.7, right? So VO is, this is the 0.7, 0.7. So here, whenever, in the two cases, in both the cases, right? So if Vi is less than 2.7, then the equation is VO equal to Vi minus 2, which is, so this will be the case where the slope is 1, because VO is 1 cross dot Vi, 1 into Vi, so the slope will be 1. And in the second case, whenever Vi is greater than 2.7 volt, then the slope will be, here you can find, here we derive 2 by 3 into Vi, so the slope will be 2 by 3, right? So here it will be 2 by 3, and in exactly 2.7 volt, the value of VO will be 0.7 volt, right? So the correct answer will be answer D, this one, and this is the answer. So you understood, right? Do you have any question?
Yes, yes,
Okay, fine. So I'm moving forward to the next question. So now, compared to the previous question, this voltage 2 volt, the direction of the 2 volt is opposite, right? Here it is, this side is plus, this side is minus, and here this side is negative, this side is positive, right? So I will solve the question again using this condition. So how we can proceed? So suppose, so we will consider the first case, the diode D equal to off. So this is the diode, so D is equal to off, right? Now what is happening? The equivalent circuit becomes this. This is open circuit, this is Vi, so this is 1k, this is 2 volt, and this is 2k. Okay, so here the voltage appears as Vi plus 2, right? This is plus, this is minus, so Vi simply plus 2i. The no current is flowing in the circuit, so that's why there will be no voltage drop across this 1k resistor. So simply this voltage Vi will add up with 2, and it comes in this node, right? A, this is A, this is node B. So now similarly, so Va minus Vb should be less than 0.7 volt, which is the cut-in voltage of the diode. Then the diode will be off. So Va minus Vb, so Va is Vi plus 2 minus VB is 0, 0 is less than 0.7, so VI should be minus 2 plus 0.7, which is Vi less than minus 1.3. So whenever Vi is less than minus 1.3, then the diode will be off. And then what will be the VO? VO will be simply Vi plus 2, right? No current will be flowing in the circuit, so Vi will add up with 2 and it appears as a output voltage. This is the first case. Okay, in the second case, so if the diode is on, then the equivalent circuit becomes 1K. This is 2 volt. Here it is 2K, and we will replace the diode with this 0.7 volt potential. 0.7 volt, yeah. So now here it is VO, that is output voltage, and this is the input voltage, right? So now VA, so the diode will be on when VA minus VB is greater than 0.7 volt, right? So similarly, we can write Vi plus 2 minus 0 is 0.7 volt, which is Vi is greater than minus 1.3 volt. So 1.3 volt is a transition from in which the diode turns on, right? So now the VO, how we'll calculate the current throughout the circuit. The current flows like this, current I. So I is nothing but Vi plus 2, which is adding up, right? And it is minus 0.7 divided by 1 plus 2, right? So it will be 3. And this current is flowing through 2K resistor, so this voltage will add up with this. So VO ultimately becomes 0.7 plus I into R, right? So here we can write this as Vi plus 1.3 by 3. It will be 2 Vi is 0.7 into 2K ohm resistor into Vi plus 1.3 divided by 3, which is 0.7 plus 2 by 3 Vi plus 2 into 1.3 by 3. So this will be the VO. So this will be the VO. Okay. So if we want to plot this, this is Vi and this is VO. This is known as transfer characteristics. Transfer characteristics. The output voltage with respect to input voltage. So the transition happens when this the value of Vi is minus 1.3. So it is, the value is minus 1.3, and particularly at Vi equal to minus 1.3, what will be the value of VO? VO will be minus 1.3 plus 2, which is 0.7 volt, right? Similarly, if you put into this equation, then also it will come VO equal to 0.7 plus 2 by 3 into minus 1.3 plus 2 by 3 into 1.3. So these two cancels out, so this is 0.7 volt. That means this graph should be continuous, right? So at minus 1.3, the value of VO is, this is the value, this is 0.7, right? So if Vi is less than minus 1.3, then VO will be Vi plus 2. VO will be Vi plus 2. That means Y equal to mx plus c curve, right? So here what will be the slope? Slope is nothing but 1, right? So it is 1. And then in the next case the slope is, this is 2 by 3 into Vi, right? So the slope is 2 by 3. This will be like this, 2 by 3. Okay. So this corresponds to this diagram. So the correct answer will be answer B, right? Okay. So do you have any question? Okay. If not, then I will proceed to the next question. Yeah. So here the direction of the diode is opposite. Here the diode is in the opposite direction, right? So this terminal is N and this terminal is P. Okay. This is the diode D. So here also we will solve when diode will be off in the case 1, then the equivalent circuit becomes 1K. This is 1K. This is 2 volt. This is 2K. Sorry, in the off case, so here will be the 2K and here the diode will be off and here will be the VO. Similarly here it will be the VI. So plus minus. So here it will be VI minus 2. So now this side is P, right? So this is anode and this is the cathode. So the cathode terminal is connected to this and anode terminal is connected to this. So the diode will be off if Va minus Vk, anode minus cathode, is less than 0.7 volt. So anode is nothing but 0 volt, right? Because it is connected to ground. And this cathode terminal is Vi minus 2, that is 0.7 volt, right? So if we multiply minus in both the side of the equation, it becomes this, right? So this less than sign will be changed to the greater than, right? And the minus will be multiplied. So now Vi will be 2 minus 0.7, which is nothing but greater than 1.3. Okay, so it will be 1.3. Okay, so this is the case, and then this VO will become, then VO will become nothing but Vi plus 2. So this is the case. Okay, and in the second case, the diode, consider the diode is on. So if the diode is on, so here will be 1K, here will be 2 volt, this is plus minus, here will be 2K, right? And here this terminal, anode terminal, is positive, right? P, and this is N, right? So this thing will become positive and this will become negative. So this is plus, this is minus, this is 0.7 volt. This is VO and this is VI. Okay, so now, so diode is on, that means Va minus Vk should be greater than 0.7. So that means 0 minus, what is the value of cathode? That is Vi minus 2. should be greater than 0 0.7. It will come Vi is less than 1.3. Okay, so whenever the diode is on, then what will be the current? The current will be I is basically this Vi minus 2 plus 0.7, because the 0.7 is adding the current, right? The positive terminal is in the downside, right? And here this is opposing the current, so this will be minus. So Vi minus 2 plus 0.7 divided by 3, that means Vi minus 1.3 divided by 3. So what will be the output voltage in this case? Now the output voltage will be twice into I, that means the current flowing in this direction, and minus 0.7 volt, right? So minus 0.7 volt, this is the 0 volt potential, this is minus 0.7 volt, and this is minus 0.7 volt plus 2 into I. So 2 by 3 into Vi minus 2 by 3 into 1.3 minus 0.7. So this is the case. Okay. So what will happen when Vi is exactly equal to 1.3? So we will put here, so VO equal to 1.3, sorry, I think 1.3, yeah. So okay, I think I have done mistake here. Okay, yeah. So this VO will be Vi minus 2, right? Because this is positive terminal, this is negative terminal. Okay, so if I put in this is 1.3 minus 2, which is nothing but minus 0.7 volt. So similarly in this case also it will come as VO equal to minus 0.7 volt. So if we plot the graph, so this is VO, this is Vi, then the transition happens at 1.3, so this is 1.3. So what is happening, whenever the Vi is greater than 1.3, it is V equal to Vi minus this. Okay, at first of all, at 1.3 the value of the VO is, this is VO is minus 0.7 volt, right? So here it would be the case. So whenever Vi is less than 1.3, that means Vi is less than, means in this side the slope will be 2 by 3, right? 2 by 3 into Vi, so it will be 2 by 3, and then the slope will be 1, because here in this case it is 1. V equal to 1 into Vi minus 2, right? Into 1. So the correct answer will be answer A. So answer B will not be the answer, because here at this transition voltage is like minus 1.3, but it is coming as 1.3, right? So you can eliminate one of the answer by seeing this equation. Okay, yeah. So do you have any doubt? Okay, so I will solve the next part. So case 1, D equal to off, the equivalent circuit becomes 1K, this is 2 volt, this is 2K, this will be open, and this will be the case. Okay, so here it will be Vi plus 2, this is plus, this is minus, and here it will be the ground. So B is off, right? So this V anode minus V cathode should be less than 0.7. V anode is 0 minus Vi plus 2 less than 0.7 multiplying minus sign in both the sides greater than minus 0.7. So Vi should be 2. So this will be minus 2.7. Then the value of VO will be Vi plus 2, right? Okay. In the second case, the diode will be on, so the circuit becomes 1K. This is 2 volt, this is 2K, and here also it is a negative terminal, it will be the positive terminal because it is P and it is N, right? So minus plus, this is 0.7, this is VO, this is Vi. So this is Vi plus 2. So similarly, the diode will be on when Va minus Vk should be greater than 0.7. So it will be 0 minus Vi plus 2 will be greater than 0.7. So it will come as Vi less than minus 2.7. Okay, then what will be the value of Vo? The current flow will be I. So the current I will be Vi minus, so sorry, Vi plus 2 because 2 is adding the current and it is also adding, so it will be 0.7 divided by 3, which is nothing but Vi plus 2.7 by 3. So this Vo will be 2 by 3 Vi plus 2 by 3 into 2.7 and minus 0.7, right? So minus 0.7 is the potential at this node plus the voltage drop across this resistor. So this will be the thing. So what will be the Vo at exactly 2.7 volt? Vo is minus 2.7 plus 2, which is minus 0.7. So if we plot this thing, minus 2 points, this is Vi, this is Vo, this is nothing but minus 2.7, and at minus 2.7 the value of Vo is minus 0.7, right? So this is minus 0.7, so here it will be the point. So whenever Vi is less than minus 2.7, the slope will be 2 by 3, and above that the slope will be 1 because Vo is Vi plus 2. So the correct answer will be answer B, right? So this is 2 by 3 here, and here it will be 1. So the correct answer will be answer B. Okay, so do you have any question? Okay, so the next question, uh, in the circuit shown in the figure, Vi is increased starting from 0 volt. At what value of Vi will the diode turn on? Okay, so this is the characteristics of the diode. So this means whenever the cut-in voltage is 0.7 volt, and basically this from this IDVD curve we can calculate the uh, on resistance of the diode. So basically here we can see that there is no slope, so the on resistance R on will be nothing but 1 divided by slope. So here the on resistance is 0 basically, right? So the equivalent diode symbol can be replaced by this thing when the diode is on, and it will be open circuit when the diode is off, right? Because in the negative terminal the current is 0, so it will be the open circuit, and whenever it is greater than zero point 0.7, so we can write this diode symbol as 0.7, right? Okay, so now in the question it is asked that vi is increased from 0 volt. So at what value of vi the diode will turn on? So consider the diode is off, so d equal to off, diode is off. Then what is the voltage across this node? This is va, this is vb, which is, this is the anode, this is the cathode, right? So va, the voltage va is nothing but vi. Apply the voltage divider rule. So vi divided by 2 plus 2 plus 1, which is 2 by 3 vi. This is the va, right? And this is the vb. So if the diode is off, then this terminal vi, so 2 by 3 vi, so va minus vb should be actually as the diode is off, so this vb, there is no connection, so vb is connected to ground, so vb is 0, vb is 0, and the diode will be turned on when va minus vb is greater than zero point 0.7 volt. That means 2 by 3 vi minus 0 should be greater than zero point 0.7 volt, so vi should be zero point 0.7 multiplied by 3 divided by 2 is 0.21 divided by 2, sorry, 2.1 divided by 2, which is 1.05 volt. So whenever this voltage vi becomes 1.05 volt, then the diode becomes on, then the diode turns on, right? So this will be answer C, 1.05 volt. So how do we generally calculate? We consider the diode to be off at first, and then we find out the potential across the diode. What is the anode potential and what is the cathode potential? Now to turn on the diode, the anode potential minus cathode potential should be greater than the cut-in voltage, right? So Va minus Vb is 0.7 volt, and from there we get the value of the Vi, which is nothing but 1.05 volt. Okay. So in the second question, it is asked that in the same circuit, what will be the value of the V3 if Vi equal to 5 volt? So far we know that whenever the Vi is greater than 1.05 volt, the diode becomes on, right? So in this question, it is asked when Vi equal to 5 volt. So 5 volt is obviously greater than 1.05. So we will consider the diode to be on, and we replace the diode to the equivalent model, right? So this circuit can be redrawn as, this is the Vi, this is 1k, this is 2k, right? And here the diode will be replaced by its equivalent model, which is 0.7 volt plus minus, and here it is another 2k, right? So the voltage across this output port is referred as V3, and here it is referred as V2, right? So now what will be the voltage across it? So it will be, so here we apply so it is this is the super mesh. So if we consider this as, okay, so the current flowing in this direction, we are applying the KCL. So V2 minus Vi divided by 1, the current flowing in this direction, plus V2 divided by 2, the current flowing in this direction, right? Plus the V3, the current flowing in this direction is V3 divided by 2 is equal to 0. And we have one more equation, like if it is V2, it is V3. We know that V2 minus 0.7 equal to V3. So we replace the value of the V3 in this equation and we get, so V2 minus Vi plus V2 by 2 plus V2 by 2 minus 0.7 by 2 equal to 0, right? So V2 plus this V2 by 2 and V2 by 2 turns V2, and this Vi goes to the opposite side 0.35. Okay, so 2V2 equal to Vi plus 0.35 and V2 is Vi by 2 plus 0.3.5 by 2, right? And in the question it is asked what is the value of V3. V3 is V2 minus 0.7. So in V2 we write Vi by 2 plus 0.35 by 2 minus 0.7. Okay, so this Vi is 5 volt, right, according to the question. So what is the value of V3 when Vi equal to 5 volt? So then it will be 5.35 divided by 2 minus 0.7, 5.32.67 and then 10, that is 5, yeah, minus 0.7. So it is close to 2 volt, right? So the correct answer will be 2 volt. Okay, okay, you understood this? Hello? Yeah, okay. So now to the next question. In the same circuit, what is the slope of the V3 versus Vi at Vi equal to 5 volt, right? So the actually we have already derived this thing. So whenever there is V2, so V3 is nothing but so V3 is V2 minus 0.7, which is Vi by 2 plus 0.35 by 2 minus 0.7. So Vi by 2 plus some constant, right? So now what is the slope? So how can we find the slope? This is if we do the derivative of V3 with respect to the input, right? So we can get the slope. So this is nothing but half. So that means the or else we can if there is an equation like y equal to mx plus c, so m is the slope, right? So V3 equal to half of Vi plus some constant which is nothing but c. So this half will come as a slope. So dV3 dVi is nothing but the slope, which is 1 by 2. So the correct answer will be answer D, which is 1 by 2. Okay. Okay. So the next question is, in the circuit shown in the figure, V1 is 0.7 volt when both the diodes, for both the diodes. So this is basically the Zener diode. So what happens to the Zener diode? So Zener diode is nothing, it operates like a normal diode, but it has an extra operational condition, which is when the Zener is in breakdown in the breakdown region, then it gives the constant voltage, right? So then it can acts as a regulator also. So uh, this is a symbol of a Zener diode. So this terminal is P terminal, this terminal is N terminal, right? This is anode and this is cathode. So in this terminal, the voltage is VA, let's say, and this voltage is VK, right? So so how can we write the model? So whenever VA minus Vk is greater than is 0.7 volt, this is the normal, it can act as a normal diode, right? So minus 0.7 volt, then the diode, this is Zener diode becomes on, okay, and then we can replace it by its equivalent model, which is R on the on resistance and also this cut-in voltage 0.7 volt, okay. So this is one model, and in the second case, suppose VA minus VK is, or in the other way we can write as the if we apply the cathode, the voltage in the cathode terminal, that is Vk minus Va anode terminal is greater than the breakdown voltage. Suppose here it is 3 volt, so it is different for different materials. So let's say the Zener voltage is 3 volt, so if it is greater than 3 volt, then this Zener diode is in reverse breakdown region, right? So what happens is it can be written equivalently. So this 3 volt will come across this thing, and there will be some resistance. So R is some resistance, and this 3 volt will come in this. So then this diode, so this diode can be represented this model whenever this is 0.7 volt, and whenever this is greater than 3 volt, this diode can be modeled by this, right? Okay. So in some cases, if we ignore the add-on, then this equivalent circuit becomes this the model becomes this, and if we ignore this also, then we can represent it as short circuit, okay. And here also, if we ignore the resistance, because on resistance is very less, and sometimes what happens, if we apply a very large voltage and this 0.7 volts is so negligible that we can ignore that. So that's why I ignored in the this case, and it appears as a short circuit. But if it is, hello, hello, am I audible?
Hello.
Yeah, am I audible?
Yes, sir.
Yeah, yeah, okay, okay. Yeah. So if so this on register so when this Zener works as an in breakdown region, then also it has a very small amount of resistance. So if we ignore this R also, then it will come like this, right? 3 volt, okay. So actually you should apply the model according to the question, or according to the input given in the question, right? Okay. So and in the third case, whenever this this Vk minus Va, that means cathode is more positive than anode, right? It's greater than 3. So we can also denote in the other way, like Va minus Vk should be less than minus 3, right? if we multiply negative in both the sides, right? Okay, so that means when VA minus VK is less than -3, then this is in the reverse breakdown region, and when VA minus VK is greater than 0.7 volt, then it acts as a normal diode, that means in the on condition. Okay, and if it falls in this region -3 volt to 0.7 volt, then it acts as an off condition, right? So R off, and this off resistance is very high, so you can written as an open circuit. So the Zener diode has three operating condition. One is normal on, like the diode, and other is off, normal off condition, and the third region is the in the reverse breakdown region. It gives a constant voltage of 3 volt. Okay, so in this question it is asked that this V on is 0.7 volt. That means this diode also, when on, it offers 0.7 volt, and this Zener diode D1, when it is on, it also offers the same voltage, 0.7 volt. And for this particular Zener diode, it has a separate operating region which is 3 volt, right? So what is the slope of DVO versus DVI? That means what is the slope of output versus input, or the transfer characteristics when only D2 conducts? So when only D2 conducts, the equivalent circuit becomes, when only D2 is conducting, so D1 is not conducting, so we will not take D1 in the picture. So VI 1.8k, so this is open and this is conducting, right? Yeah, so D2 is conducting. That means we can write the equivalent model like this. Okay, so this is 3.3k and this is 0.7 volt. So what will be the VO? So now what happens, we just apply a simple KCL in this circuit, right? VO minus VI divided by 1.8, that is the current flowing in this direction, plus VO minus 0.7 divided by 3.3, that should be equal to 0. That means VO divided by 1.8 plus VO divided by 3.3 equal to VI by 1.8 plus 0.7 by 3.3. Yeah, just try to solve without calculator only. You just use calculator when it is needed, right? So VO, if we take common, 1 divided by 1 plus 8, 1 divided by 1 by 3 equal to VI 1 plus 8 plus 0.7 by 3.3, right? So VO will be this goes there, 1.8 into 3.3 divided by 1.8 plus 3.3 into 1.8 plus some constant value, right? So I am writing as constant because in the question I have to uh, find out the value of DVO DVI. Okay, so this will not the constant will become 0, right, if we take the derivative. So I am not worrying about this constant value. So now this 1.8 cuts out, so VO turns into 3 by 3.3 divided by 1 plus 8 plus 3.3, 8 plus 3 1, 5.1. Okay, so 3.3 divided by 5.1, how much it is coming? 3.3 divided by 5.1, so 0.647 or 0.65, so it will come as 0.65. So the correct answer will be 0.654. Okay, okay, so do you have any question?
No, sir.
Okay, so in the second case it is asked what will be the slope, the same dvo versus dvi, when now the d2 is conducting in the forward direction, and as well as this d1 is conducting in the reverse direction. Okay, so the Zener is particularly operating at the breakdown region, and d1 d2 sorry d2 is normally in the on condition. So the equivalent circuit becomes, so this will be the 1.8k, this is vi, and then the d1 is reverse direction, so here it will be plus, here it will be minus, and it will be 3 volt, because it's already given in question 8, right? So what is the value of the vz? It is 3 volt, right? Okay, so this is 3 volt, and then here it will be 2.2, this is ground, and then here also it is 0.7 volt, right? This is the p and this is the n, right? And this is also the p and n, but it is operating in the reverse direction, so that's why here it should offer in the opposite direction. Okay, yeah, so here it will be 3.3, right? So now this voltage is vo. So now we apply the same KCL method. So the current flowing in this direction is nothing but vo minus vi divided by 1.8, plus the current flowing in this direction is vo minus 3 divided by 2.2, plus vo minus 0.7 divided by 3.3 is equal to 0. So it will be vo 1 divided by 1 plus 8, 1 divided by 2 plus 2, 1 divided by 3.3, and taking in the other side vi divided by 1 by 8 plus some constant, right? Okay, so vo, this is 1.8 into 2.2, 3.3, 2.2 into 3.3 plus 1.8 into 3.3 plus 1.8 into 2.2 equal to vi divided by 1.2. 1.8 cancels out. vo is vi into 2.2 into 3.3 divided by, so what is 2.2 into 3.3? So 2.2 into 3.3, it is 7.26. So this is 7.26 plus 1.8 into 2.2, this is 3.96. So this will be 3.96 plus 1.8 into 2. Okay, I am using the calculator actually. Okay, this one is 5.94. 5.94. So now if we do dvo versus dvi, so it will come 2.2 into 3.3, it is 7.26 divided by, if we add this will come 17.16, so it is close to 0.42. So yeah, so this will be the answer, right? Okay, okay, so if you have any doubt, then you can ask. Yeah, so I am moving forward to the next question. So now it is asked, like, when d1 conducts in the forward direction and d2 doesn't conduct, so it will be like the same, like 1.8k. So d1 conducts in the forward direction, so that means d1, so that means d1 is acting as a normal diode. Okay, that is the normal diode. Normal diode means here it is the p terminal, here it is the n terminal. Yeah, so it is the p terminal, and here it will be the N terminal. So this is positive, this is negative, this is 0.7 volt, this is plus, this is minus, this is 2.2, and this side it is open, right? It is 3.3. So now this will be VO, this will be VI. Okay. Similarly, we can apply the KCL like VO minus VI divided by 1.1.8, which is the current flowing in this direction. And now in this direction, it will add up, right? Plus VO plus 0.7 divided by 2.2 is equal to 0, right? Yeah. So it will be VO divided by 1 plus 8 plus VO divided by 2.2 is equal to Vi divided by 1 plus 8 plus some constant term. That means this VO is 1.8 into 2.2, 1.8 plus 2.2, right? This is the plus, equal to Vi into 1.8 plus some constant, right? So VO is 1.8 into 2.2, 1 plus 8 plus 2.2 comes out as 4 into Vi plus some constant, right? So sorry, here it will be 1.8, 1.8 cancels out, 2.2 by 4 Vi plus some constant, it is VO. So this dVO by dVi is 2.2 by 4, that means 0 0.5, 20 and then 20, that's 5, 0.55, yeah. So it will be, the correct answer will be 0.55, answer C. Okay, yeah. In the next question, so this is the like the different question. It is asked like d1 start when what is the value of vi for which the d1 starts conducting in the reverse direction. That means d1 is basically in the off condition, right? So when it will conduct in the when then, so what I have already told, when D1 is off, then find out the voltage across the two terminal of the diode. So here it is the anode terminal A, sorry, this is the anode terminal A, and this is the cathode terminal K, right? So when the diode conduct in the reverse direction, then Vk, that means the cathode terminal minus anode terminal, should be greater than the Zener breakdown voltage, which is 3 volt. So Vk minus Va should be greater than 3, right? Okay. So it will be greater than 3, right? Now what happens? It is greater than 3. Now what is the value of Vk? So Vk is basically V0. This is the V0 minus anode terminal is connected to ground because this is off, D1 is off initially. So V0 should be greater than 3 volt. So whenever V0 is greater than 3 volt, then only it conducts. So whenever the D1 starts conducting, this V0 equal to 3 volt across appears in this direction, right? This 3 volt, yeah, in this node. So now what is the value of Vi? So Vi, so if it is 3 volt, VO equal to 3 volt, then this D2 is also turns on because it is 3 volt. If it is off, if we assume that D2 is off, then this anode terminal is 3 volt and this cathode terminal, which is this one, this cathode terminal is 0 volt. So Va minus Vk, cathode minus anode minus cathode, which is 3 volt, that is greater than 0.7 cut-in voltage. So so D2 should not be off, that means D2 should be on condition, right? So if D2 is on, then the circuit becomes like this is 1.8k, this is Vi, and this is just turned on, right? So and here it is, so this terminal is positive, right, P, and this terminal is negative, right, N, right? So this will be the case, yeah. So 0.7 volt, and here it will be 3.3k, and here there are the rest of the circuits, yeah, right? It is 2.2k, it is D1, right? So here we have calculated the value is 3 volt, VO is 3 volt. So the current flowing through this is I, the I should be 3 minus 0.7 divided by 3.3, that is 2.3 divided by
मी आले आले
3.3.
बघून तिचा हसत होते. म्हणलं मी फोन केलता तुला, तू फोन नाही रिसीव्ह केला, मग म्हणलं झोपली असेल, जाऊ दे, जातो आता घेऊन जाऊ. मग मी आले.
Okay, so so the current I will be 2.3 divided by 3.3, and so this terminal actually D1 on just only starts conducting the reverse in the reverse condition. That means the current we can consider 0 just before conducting. So this whole entire current I should pass through the 1.8 kilo ohm. So now this is 3 volt. So Vi minus 3 divided by this resistance 1.8, it is coming as 2.3 by 3.3, right? So Vi is 2.3 divided by 3.3 into 1.8 minus 3, right? So so how much is coming? Vi is nothing but it comes out as 4.254, sorry, so 4.254 volt. Okay, so the correct answer should be answer C. Yeah. So yeah, the next question, an input voltage VIT is V1 plus Vm sine omega t. Okay, so this is applied to the circuit shown in the figure. So this figure, so if V1 is 0.7 volt, that means whenever the diode is on, 0.7 volt potential appears across it, right? And then V1 is 3 volt and Vm is 4 volt. Vm is 4 volt. Okay, so VIT we can write as 3 plus 4 sine omega t. Okay, so what is the so yeah, so how to draw this graph 3 plus 4 sine omega t? So this is basically is a graph of sine omega t with respect to omega t. It varies from 0 to it varies from 1 to minus 1, right? So what is the graph for 4 sine omega t? So the amplitude will be multiplied by 4, right? So here it will be 4 and here it will be minus 4. Okay, and now in this case this is 3 plus 4 sine omega t, so this signal is shifted by positive amount of 3. So this is 3 volt. So 3 plus 4 is 7. So suppose this is the 7 volt, and 3 minus 4 is minus 1. Suppose this. So now okay, so that will be the voltage. So now this voltage, so this voltage is appearing is applied to the circuit. So if V1 is 0.7 volt, so the circuit, now the circuit, if I redraw the circuit, so I am redrawing the circuit. Yeah, so what will be the value of so if the diode is on, then only the current flow through this path, and then only the capacitor can charge. So this diode, if we consider is D equal to on, then only this terminal will connect to plus, and the current will flow through this, and this terminal capacitor, this plate will gain the positive charge, and this terminal will negative charge. Okay, so if the diode is on, now what is the, this is the anode terminal and this is the cathode terminal. So VA minus VK should be greater than 0.7 volt, because it is mentioned in the question V1 is 0.7 volt. This is the V1. V1 is 0.7 volt. So whenever this condition occurs, then only it will come. So what happens? That means so now initially the anode is 0 because no current is flowing through this, minus Vk. Vk means Vk is nothing but that voltage across the cathode, that is Vi. So we can replace this Vk by Vi is greater than 0.7 volt. That means Vi should be less than minus 0.7 volt. So whenever Vi, the voltage across the input terminal, is less than 0.7 volt, then only the diode starts conducting. So I am putting a reference line here. Okay, sorry. So this is minus 0.7 volt. So when Vi is 3 volt, then the circuit is the current is not flowing, and throughout this cycle it is not flowing, and until this point this is not flowing. After this minus 0.7 volt, the current start flowing, right? So now the capacitor, if we consider the voltage across capacitor is Vc, then if it becomes minus 0.8 volt, then also the current flows, because whenever Vi is less than minus 0.7 volt, so throughout this cycle the current flows till this maximum value. Now the time constant of the circuit is nothing but Rc. So R is basically the on resistance of the diode. So on resistance of the diode is very small, so this tau is basically on resistance into the capacitance value, and as the on resistance is small, so tau is very small. That means the capacitor charges instantaneously, right? So what happens, this Vc, this Vc becomes, this is 0.7 volt. So this becomes this charges becomes till Vi becomes minus 1 volt, the capacitor charges, and then the capacitor then after this minus 1 volt, the diode becomes turned off, and the capacitor the voltage across the capacitor remains the same, right? So this is basically a problem of peak detector. That means using this circuit we are detecting the peak, and if it is this 1 volt, so and the diode has zero point 0.7 volt, so zero point 0.7 minus 1 volt, that will appear in this that is the output terminal VO, sorry. Yeah, so this and this becomes the constant 0.3 volt, right? So VO will be minus 0.3 volt, and that will be the constant, because after reaching the peak value, the capacitor the voltage across the capacitor does not change, right? So this is the case, right? Okay. Okay, so moving to the next question. So this is a circuit of a voltage regulator. So here we are applying a input voltage. A simple voltage regulator circuit is shown in the figure, and to ensure the proper operation, the Zener diode, this the voltage across this VZ is 10 volt. That means this terminal should be plus, this terminal should be minus, right? It is 10 volt, and it requires a minimum current of 10 ampere. That means whenever the Zener diode is on, the current flowing through the Zener diode should be greater than 10 milliampere, and then the maximum power dissipation of the Zener diode, that means P max across Zener diode is 1 watt. Okay, so if the maximum power dissipation across the Zener diode is 1 watt, then the maximum current across the Zener diode, that will be, so this will be P max divided by voltage across the Zener diode, P equal to V into I, right? So this is 1 watt divided by Vz, that is 10 volt, that means 0.1 ampere, which we can refer as 100 milliampere. So the maximum current that can be passed through the Zener is 100 milliampere. So the minimum current is required is 10 milliampere, and the maximum current is 100 milliampere. Okay, so now the question asked that the maximum power dissipation, so if the input voltage can vary, input voltage is varying from 12 volt to 15 volt, then what minimum value of R is required? Okay, so the Zener is acting as a voltage regulator, so this 10 volt is appeared across this load resistance RL. So the current through the RL, if we referred as IRL, then the current through the RL comes out 10 volt divided by 1.5 1.5k, which is 10 divided by 1.5 milliampere. So this much current is flowing through the load resistance, right? This is the load resistance. So now here if we apply the KCL, so here in this case, this value, yeah, so if we denote the current flowing through the resistance R is IR, then the IR, the load the current, that should be less than 100, because if we sorry plus 10 by 1.5. So 10 by 1.5, this much milliampere current is flowing through the load resistance, and maximum the Zener diode can uh, the maximum the current that can be flown through the Zener diode is 100 milliampere. So the total current that is flowing through the resistance R, that should be always less than equal to 100 plus 10 by 1.5, right? So now this IR, that is the current flowing through the resistor R, can be written as VI minus, this is the 10 volt, right? So VI minus 10 divided by the value R, and it should be less than 100 plus 10 by 1.5, right? Okay, now we can so I am rewriting this equation. R should be greater than Vi minus 10 divided by 100 plus 10 by 1.5. Okay, okay. So now the Vi is, so the Vi is 10 volt to 12 volt to 15 volt, that is given in the question. So for Vi equal to 12 volt, the resistance R should be 12 minus 10 divided by 100 plus 10 by 1.5. So this is 100 by 15, right? So this is 12 minus 10, so R should be greater than 2 divided by 1500 plus 100 divided by 15. That means R should be greater than 2 divided by 1600, and this is the 15. Okay, so this much kilo ohm. Okay, so this is the one condition, and in the second case, for Vi equal to 15 volt, the resistance R should be 15 minus 10 divided by 100 plus 100 by 15. That means R should be greater than 5 divided by 1600 by 15. That means R should be greater than 5 into 15 by 1600. So look, this is the value, this is the lowest value, that is 2.15, and for V input is equal to 12 volt. This is the requirement of R, but if it operates it at 15 volt also, then the value of R is much more above than this value. So we should always consider this value, so that the circuit can operate at a higher voltage. So for this case, the appropriate resistance should be 5 into 15 divided by 1600 kilo ohm. Okay, kilo ohm means we can multiply 1000, so these two cancels out. This is 5, this is 8, right? So R should be greater than 25 into 15 divided by 8. So R should be greater than 25 into 15. So 5, 25, 5, 12, 25 plus 12, 37. Yeah, 37 divided by 8. So R should be greater than 4, and then 5, 5, 4, 7, 8, 6. Okay, so it is near about 47 ohm. Yeah, so the correct answer will be answer A. So which is nothing but 47 ohm. Okay, so do you have any question till this point? Hello. Okay, understood, right? why this maximum actually, when when we go to buy any diode like Zener diode, then there is written like maximum power, because the actually I am discussing one thing. Yeah. So suppose in the diode characteristics we have seen, like this is the IV characteristics. So the current becomes very high after its cut in voltage, that is 0.7 volt after this, and it is very low in this reverse bias, and it suddenly in the breakdown voltage the current becomes very high, right? So this is the, we can refer it as breakdown voltage. Okay. So in the breakdown voltage, ideally, that means with a small change of voltage, the current flows very large, right? But there should be some limitation, right? Because if the current is not limited, then the power across the device becomes very high. So I into VVR, and this, if this I is very high, then what happens, it multiplies with this V and becomes a very high amount of power. So this amount of power transfers into heat, right? So whatever power that is generated, that transfers into heat, and that can damage this device, right? So there should be some limitation. So the limitation in case of diode, or suppose any resistor or something, it is always written in terms of the power. That means by this power you can also you can always calculate that whatever the maximum current that can be flow through the through that Zener diode, because you know that breakdown voltage or at what voltage the diode is operating. So if you divide the power with this voltage, and if we get the current, and then if we get the current, so at that maximum till that current it can basically the Zener diode can withstand. Okay. Yeah. So what happens if so here I have limited I have written this equation like the current flowing through the R, the resistor R, that should be less than equal to 100. Why? Because this is fixed, right? This is the 10 volt, that should always be appear when the Zener diode, this Zener diode is acting as a regulator. This 10 volt will always appear in this, throughout this, right? So there is no voltage fluctuation across this load resistance. Load resistance means you can load resistance means you can attach a speaker or something. There should be, so every that every device should have some resistance, right? So the voltage across that device, that should not be changed, that should be regulated, right? So this Zener diode acts as a regulator. And now what happens, that if this now so there will be some fixed amount of current that is flowing through this load resistance, because it is 10 volt, right? And it has some resistance, this device has some resistance. Suppose for this speaker it has 25 ohms, suppose this resistance. So there should be some limited amount, the fixed amount of current that should be flowing. And if the value of the resistor, so here we have found out, right, the resistance should be greater than 47 ohm. So if the resistor becomes very small, less than 47 ohm, that means this is the voltage, right? Here we are applying 15 volt, here it has 10 volt. So there is a potential difference of 5 volt always. And now if we decrease the value of the resistance, then the current will be huge, and so the current will increase. And this increased amount of current, there is a fixed amount of current that should flow through the load resistance. So uh, the rest of the current, that should always flow through this Zener diode. But Zener diode has some limitation, right? That has some maximum power that it can withstand. So if we apply more and more current, then this 10 volt into that more current, that will be greater than this power rating of this Zener diode, and the Zener diode will become damaged, right? So that's why we limit the we always mention the maximum power limit of the Zener diode. Okay. Yeah. So this is the last question. So for the regulator circuit, same regulator circuit, what is the maximum value of R? So so far we have calculated what is the minimum value of the resistance, that is 47 ohm. And now it is asking like what should be the maximum value of resistance for which the circuit will act as desired. Okay. So now uh, we will do in the same way, right? Like if the voltage, if this Zener diode acts as a voltage regulator, then always a constant voltage of 10 volt appears across this Zener diode. So now the current flowing through this load resistance is 10 volt divided by 1.5 k. That means 10 divided by 1.5 milliampere, right? Okay. So this current always flows through this load resistance. Now the here in the question it is already mentioned that it requires a minimum amount of current 10 milliampere, the Zener diode, without which it cannot operate. So here it will be 10 milliampere and here it will be IRL, right? So 10 milliampere at least it should flow. So the current flowing through this resistance, that is IR, that should be always greater than 10 plus, because this is the fixed amount of current which is flowing. This is the fixed amount of current 10 divided by 1.5 that is flowing through this. So and here it is for the operating condition of the Zener diode, the current should flow 10 milliampere through it. So the IR value should be greater than this. So this IR value can be written as VI minus 10 volt greater than 10 plus 100 by 15. Okay, that much milliampere. Sorry, VI minus 10, that is the current, right? So VI minus 10 divided by R, right? So that is the current here. So that should be greater than this. So in the other way I can say R should be less than VI minus 10 divided by, this is 10 plus 100 by 15, right? So R should be less than 15 into VI minus 10 plus 1600, right? Yeah. Now there is a there is case 1. If Vi is 12 volt, then the value of R should be 15 into 12 minus 10 divided by 1600, that much kilo ohm, right? So R should be less than 15 into 2 divided by 1600 kilo ohm. This is one case. 15 into 2, right? Okay, yeah. And the case 2, if the input voltage is 15 volt, then the resistance R should be 15 into 15 minus 10 divided by 1600, that much kilo ohm, which is nothing but R should be less than 15 into 5 divided by 1600. So if the so to operate throughout this voltage 12 volt to 15 volt, the resistance value, this has some resistance value, but this resistance value should be is much lower than this value. So we should always consider this lowest value so that the circuit can operate throughout 12 volt to 15 volt. So the value will be 1600 oh sorry, it will not be 1600, sorry, this is 15, right? So 150 plus 100, so it will be 150 plus 100, that means 250. So resistance value 15 Vi minus 10 divided by 250. So here it will be 250, here it will be 250, here also 250, 250, here also it is 250. Okay, yeah. So now here also it will be 250. So resistance is 15 into 2 into 1000, because I'm transferring it to ohm from kilo ohm, 250. So it cancels out to be 4. So R should be less than 15 into 8, 120, 120 ohm. So the resistance value should be less than equal to 120 ohm. So if it is less than 120 ohm, then only the circuit can operate from 10 volt to 12 volt. Okay, so do you have any question?
No, sir.
Okay, fine. This was the last question. So yeah, so I have completed the week 3 assignment, and in this Friday, please try to join. I will complete the week 4 previous year assignment, and that class will be taken from 6 p.m. to 8 p.m. Okay. So actually, sorry about the delay. Actually, yeah. So
Timing is same, na, sir?
sorry.
Time same, no?
Yeah, 6 p.m. to 8 p.m. Actually, I have came to ISRO for my research work, so that's why I'm not able to take the class, general schedule class, in the last Tuesday. So that will be compensated in this Friday. Okay.
Okay, sir.
Okay.
Schedule is same.
Same. Actually, NPTEL team will
Okay.
notify you also. You can see in this
Yes, sir. Yes.
announcement section. Yeah. Okay. Fine.
Reminder news.
Yeah. Sure. Yeah. So thank you. So we'll meet again in the Friday, right? Okay. Yeah.
Yes, sir.
Yeah.